Hey, calculus class. I've been just looking over the homework, the grade book, and I've just seen that there is some struggles on this one. This is one, having the ability to visualize what you're being asked to do here is really important. I want to show you just a visual of this one. This is volumes of revolution. I know there's some animations on the Moodle page, but just because of the wording of this one's a little weird. So this is that function that they give you, x equals square root of 2y squared. That's a parabola. It's just a little piece of it that I've got graphed here, but it's a parabola. And it talks about the planes x equals 0 and y equals 0. So this is a piece of software called GeoGebra 3D. It's for three-dimensional stuff, which volumes of revolution are. So y equals 0 and y equals 1 in 3 dimensions are planes. So that's what it's talking about. We've got this curve, and in between these two planes, what we're doing, this shape that they're describing happens from revolving this curve around the y-axis. And if I do that, I get this shape, which is a volume of revolution. That's what we mean by that phrase. Let me make it a little bit bigger so it's easier to see. So there it is. And then it talks about the cross-sectional disk, sorry, the cross sections are perpendicular to the y-axis or circular disk. And so just to give you that visual, if we took this shape and cut it perpendicular to the y-axis, so these, like, imagine something like these planes slicing down through there, we would get these cross sections that are circles that look like that. These should be circles. It's just the scaling is kind of making them look like ovals there. It'll probably make it look a little more circular. And at any point on that y-axis, we could slice this and we would get a different circle. And that circle, again, it's just coming from the distance. The radius of the circle is just the distance from the y-axis out to this original curve. So anyway, that's the visualization here of what we're dealing with. All right, so how do I find then the volume of this? All right, so the volume of a circular cylinder is pi r squared times h, right? And in this picture that we have, the cylinders that we're going to be talking about are basically this little green circle. If I take everything away from here, other than this green circle, you can see that what would happen if I move this point back and forth, those circles get bigger. But the radius of this circle that we get in the pi r squared, the r, is the distance from the y-axis to that curve, which is the function. That's this. So that is going to replace the r, and then the h is the differential. All right, it's a tiny little change. It's basically, in this visual, it's the width of that green little circle. It's a slight, tiny little change in the y direction. As I move left or right, this circle changes height. So it's the width of this circle. The disc, if you want to call it that. It's like the thickness, like a quarter or something, like a coin, how thick it is. That's a slight little change in the y direction. So that's what I would label as dy. A slight change in the y direction. And everything else is well, the only thing left there. It's just a constant. So that's what this thing is going to look like. I got to square it because the radius is squared. But that is how we do the disk method. It's pi r being the function, is our radius when we're doing the disk method, pi r squared, and then h, the differential. All right, and then I'm going from y, this is y, right, dy, so y equals 0 to y equals 1. And that's how I do the setup here. And then from there, it's just a calculus 1 problem now. All right, so there's the simplification. I would put the 2 pi on the outside, and then the integral of y to the fourth is y to the fifth over 5, going from 1 down to 0. Obviously, when 0 goes in, we'll just get 0. So this is just going to be 2 pi times 1 over 5, or 1/5. So 2 pi over 5 cubic units.